Hello again. Finally, we are at a point where we can start talking about the real concept that we are interested in this particular course, which is stability theory, right? So the outline of lecture will start with some motivating examples, right? I mean, the word stability has many notions in the general public, and how we are going to use it, we will eventually provide those rigorous definitions. So there are different kinds of notions of stability, and we will introduce all of them, and then eventually some generalizations of the concepts that we discuss here, but we won't otherwise provide any details in terms of results, how to check for stability of those generalizations and things like that. So we will go through several examples, right? And then we will go beyond the examples that I have on the slides. But the first one is a favorite of mine. As I record these lectures, there's a web series called Three-Body Problem, and essentially they made a science fiction out of this very famous historical problem called Three-Body Problem. When Newton discovered his gravitational law, and of course, it did not come out in vacuum. It's based on a lot of data and results developed by earlier scientists such as Galileo, Kepler, Copernicus, and whatnot. So what did Newton do? Of course, beyond generalizing to any two masses, specifically, he could explain many of the planetary motions and things like that. Right? So the inverse square law for gravitation was given, the more general three laws of motion was given, and so on and so forth. And then one simple thing that happened is, if Earth is moving around Sun, the fact that it has an elliptical orbit was clearly explained to the inverse law of gravitation by more or less solving the differential equation. And even at that time, right, the orbit of Earth, for example, was not just getting affected by Sun, but there are other planets, right? This was a known fact anyway. And the smaller planets, for example, smaller and farther planets may not really amount to much, simply because the effect of Sun's gravity is much larger than the effect coming from others, right? I mean, historically, these small deviation from what is expected orbit versus the deviated orbit was used to actually identify even more planets, right? I mean, some of these things were conjectured. I mean, they were something like 5 planets that were visible through naked eye, and then they used telescope to identify a couple more, and then eventually they identified a couple of more because of the deviation from expected orbit to the actual orbit, right? So something like Jupiter, which is the biggest planet in our solar system, of course farther, not really close to Earth, will have an effect on Earth's orbit. And how do we account for that particular, at least one planet, one more planet than just Earth and Sun itself, right? And this is the so-called three-body problem. If you have two bodies, the inverse gravitational law can be solved. You can get an equation and so on and so forth, expression for the orbits and things like that. But if you have a third body, like Jupiter in this particular case, can be solved. It turns out to be an impossible problem in terms of giving a closed form expression, and much more than that. So fast forward a little bit, and there was Laplace, and who actually showed some way of understanding the effect of Jupiter through this so-called perturbation method. And but eventually it was concluded that the three-body problem was an open problem, in the sense that nobody knew how to understand if you have three planetary bodies or heavenly bodies, just because of their gravitational attraction between each other, how do they evolve, right? And then some special cases where one of the three bodies is a very small body compared to the other two, then one has approximate solutions, and that's not really surprising. After all, if you have a third small body, that's like small deviation from perturbation from two-body problem, right? If you knew how to solve the two-body problem, then you can get approximation for the three-body problem with a smaller object there. But if you have a full-fledged three bodies that are similar size and similar weight and things like that, similar masses, then the problem of actually predicting what will happen to these three bodies under their interaction in terms of gravity, what will happen was unknown. And eventually, much later than Newton and Laplace, it was found out that these models, differential equations, turned out to be chaotic, in the sense that basically they are highly sensitive to initial condition, and basically long-term prediction in terms of what will happen to orbits of such three bodies is unpredictable, right? I mean, it's very difficult. You can predict for some short amount of time through numerical methods, but nothing beyond that. Where does this bring us in terms of stability? Well, I mean, even as these notions of how to predict the orbits were coming, people obviously were thinking also about how these solutions behave in a, do they behave in a nice manner or not, right? So one of the notions that became quite important was, Earth is going around Sun, and it's in an orbit. It's in an elliptic orbit. One of the things that we get fooled in school is basically we were told that these are elliptic orbits, but in reality, when we actually draw it on a piece of paper, naked eye cannot really probably see the ellipse nature of it. It practically looks like a circle. The eccentricity is quite small, but then it's big enough for measurement differences, right? So anyway, so this elliptic orbit, what will happen if you perturb a little bit, right? I mean, there is moon which actually has its own attraction. Of course, typically when we look at Earth's orbit, we actually consider moon as part of that system. But some other foreign body came, let's say, and then basically it pulls Earth in slightly its own, away from its orbit. What will happen? Will it come back to the orbit? Well, it really depends. I mean, if that object is actually a permanent and it has its own orbit and things like that, that's one way of looking at the problem. But on the other hand, if it is just a passing, let's say, huge body that's going away, it provides a small perturbation. So that perturbation, some deviation from the orbit, what will happen? Will it go back to the orbit or not, right? So I mean, anyway, in the case of three-body problem, that question becomes even much more difficult, simply because we don't even have a clue in terms of what kind of orbits we can get in the long term, right? There could be multiple types of orbits, and which one particular initial condition will provide is something that is practically unpredictable in long term, right? So the notion of basically whether if we are going to be in an orbit and then perturb a little bit and then come back, and that is what is stability. I mean, some kind of going back to the regime, right? And then we will look at these examples that we have seen earlier in the first lecture or so, again, and from the perspective of now the notion of stability, right? So if you recall, this particular example had something to do with controlling the level. Forget about the fact that it's a control problem. At this point, we have this system already. If you look at it, basically, whenever there is an outflow of water, this system behaves in such a way that the valve opens, right, and then water fills, right? Now, in the steady state, the water essentially reaches a particular level, and because of this floating ball and wall mechanism, it stays at that height, right? It closes the wall, and then essentially um, it stays there. And then we had a word for a system where, once it starts in a particular state and remains in that state, we call that as an equilibrium. And then in the case of differential equation, essentially that f of x of t that we keep talking about, if f of x of t is 0 at some point, and it will remain there, and then continues to be there, and then that's called an equilibrium solution. And so basically in this particular water level, if you had a small outflow, a little bit of outflow, will it come back to that equilibrium point? Will it come back to the desired height and things like that? Of course, in this particular problem, it's a very specific problem where we flush the entire tank, right? And then basically the water volume becomes 0, and then they start filling. So in that sense, basically this particular problem is such that you want to go from a particular level to another level and remain there. So in that sense, it's not quite a general notion that we want to apply there. But if you actually think a little bit more, and then it's not just for flushing, and then suppose there is some leakage somewhere, right? And then what will happen? When you have that leakage, what will happen is that leakage is going to let the water out slowly. Let's assume that it is slow. Then of course the valve will open, right? And then valve will open, and then hopefully the water input, the inlet is going to let more water than what is going out, and then at some point the level will reach the desirable height, and then the valve gets closed, right? Again, after some time it opens and things like that, and this keeps happening. And then basically essentially we see that no matter what the perturbation is, basically this height is maintained. So again, the small perturbation of this particular height will the system will actually ensure that the height will be reached in the asymptotic behavior, right? Of course, if the leakage is much more than this thing, then this we conclude that this system is unstable, right? So the James Watt's governor is again the same thing. You have this device that maintains a speed, and whenever there is a deviation from the speed, it does something to regain that particular speed. So similar notion. So you probably see the pattern that basically if you have an equilibrium point, and if you perturb from the equilibrium point, will we get back to that equilibrium point is a nice way of looking at it and calling it stable. We call that equilibrium point being stable. Sometimes there is a confusion between basically calling the system stable and then an equilibrium point stable. For this particular course, the right way of saying is calling equilibrium point, but we will talk about cases where we can be loose in terms of system versus equilibrium point, right? So the next example, again, this is an example that's part of nature and part of our anatomy, so to speak, and basically our brain controls the temperature of our body. And again, the notion of stability here is basically maintain a particular value of temperature, and if you deviate from that, can you get back? And when we have severe illness, basically our brain is perhaps not able to, or it diverts resources to fight the illness, and then this temperature maintenance may not happen. And sometimes when we are in a really cold place, the output of our the way that our body is getting really cold, the brain is unable to basically regain the healthy temperature, right? So in all these cases, basically, can you regain a particular value, right? And of course, in both water level or this one, even if it's applicable to even the James Watt governor, what we notice is there are cases where this particular value may not be reached, and that's the failure of the stability, so to speak. So how do we define our stability notion where it covers, it seems it's behaving well if the deviation of these temperatures or some small illness or something like that, or you go out in the cold, it's not really cold for our body to cope up and things like that. Those are the cases where body regains its temperature. Whereas in cases where your extreme conditions, then body gives up, right? So that means in that particular scenario it's not stable. So how do we define these various differences and things like that? We will slowly look at it, right? And then the last example that we looked at in the first lecture was flight control. And then what do we want for the flight control to do? Well, let's say for simplicity, we want to fly at 30,000 feet and remain there in spite of perturbations and things like that, right? So you want to remain there, but you could remain there if you're in vacuum. So for example, if you're in a space shuttle and you're in a particular point, you could probably remain there, but of course there are gravitational forces there, and then you may just flow along, go along a particular orbit and things like that. In the case of flight control, to start with, we are not in vacuum, and gravitation is Earth's gravitation is one of the things, but beyond that, basically you have Earth's atmosphere. Sometimes you end up in a turbulent region and so on and so forth, and then all of those things making it almost impossible to stay at a particular height, altitude, and then maintain a particular speed and things like that. So the equilibrium point, we could define something to do with both altitude and speed and velocity to be specific, and basically we can define an equilibrium point around that, and then of the entire state. And we can say that if some perturbation happen because of turbulence or something like that, can we get back to that particular point? So in all these things you can see a common theme, that basically if you get perturbed from an equilibrium point, will you get back to that equilibrium point or not, is the notion of stability, right? I want to go a little bit general and say, so if you're in a queue, let's say you're at some kind of bunch of service counters. Let's say, imagine you're in a mall, and then there are a bunch of cash counters, 3, 4, and then it's crowded. There, what is that we want? We want to ensure that we get a proper service, right? Proper service could simply mean basically we want to get out of this shop as quickly as possible. So what's the problem there? Typically they face the problem of how many cash counters should they open, right? And anyway, there are enough statistics during morning, evening, during weekdays, weekends, and so on and so forth. So let's pick some specific scenario. Weekday in the afternoon, is one counter enough, right? But what is this definition of enough? Well, of course, you can actually put some conditions, like basically no more than 5 people should be waiting at any particular time. Or maybe the condition is something like no person should be waiting for more than 10 minutes or something like that. So, but then this entire problem is random, because each person may have their own number of items, and sometimes they may have problem, the what do you call, QR code or one of those codes is not working, and then basically they have to go back and search for some other item which has that code, and so on and so forth, right? All these will make it much more difficult to even imagine the notion of stability, right? Now, one standard way of thinking about it is perhaps, I'm going to trivialize the problem and say statistically this queue should never go into infinite. I mean, it should be bounded to start with, right? So there is nothing like an equilibrium point as such there, but we just want things to be well ordered, right? So sometimes we do call such notions also stability, right? People associate, in fact, many times stability with such things also, right? In this particular course, on the other hand, we more or less restrict ourselves to the notion of equilibrium based stability notion. What else? I mean, we can think of you know examples of very different nature. So stability of an economy of a country, for example, stability of mental health, right? And stability of economy is in some sense similar to what we've been looking at, so imagine there is a equilibrium point for the entire country. That means there's buying and selling going on, foreign trade, and everything is going on. And stability means basically we can trust certain things will happen for a period of time without any issues, even if there are some small unknown aspects that happen in the system. The overall country's economy is robust enough. That means it can sustain some uncertainties and then remain financially stable, right? Again, I don't mean to define stability using the word stable, but the notion of stability is used in that fashion. And one can associate equilibrium point and then mental health, the same thing. I mean, somebody losing their mind essentially means, we are able to go through our daily activities without a lot of drama and things like that. Sometimes our brain gives up, and then it behaves in a far more erratic manner. So again, the definition of a particular equilibrium is probably very difficult in all these things, but then moving away from equilibrium and never reaching, coming back is what we call as unstable behavior of that particular system. And many times that equilibrium point could be far more general than just a point that we think of in mathematical terms, and that point may be generalized to an entire set and things like that, right? Let's say you have an ecosystem where you have one predator and one prey and things like that, and then their populations are, let's say, relatively stable. What that means is basically, there are times where the predator population may increase, and then till a point where it starts decreasing, and then basically prey population may increase, and so on. But then there is a clear-cut cycle that happens, and then if that cycle continues to be the way it is, and then even if there is a small perturbation, maybe it will come back to this particular cycle, and that's kind of an equilibrium scenario. So it's more of an equilibrium set equilibrium orbit, or whatever you want to call. So there are notions of things like orbital stability and things like that, right? So the word stable is used in a very generic fashion in general public, but for our specific purposes, we will be always talking about some kind of equilibrium, even if that equilibrium point may represent again a point in a very generic fashion, like orbits and things like that. Most of the time in this particular course, we will be talking about actually a point in your real n-dimensional space, right?